So, here's something worth thinking about as you settle in tonight. Somewhere above you, if you could see through the ceiling, through the clouds, through the last thin smear of atmosphere, there would be stars. And some of that starlight, the light landing on your closed eyelids right now if you stepped outside, left its source before you were born. Some of it left before your parents were born. A little of it left before there were humans at all, before there was anything on this planet you'd recognize as alive. It has been quietly crossing the dark this whole time, and it is only finishing its trip right now, tonight, on you. Think, for a moment, about the actual physical journey involved. That light left its source as a burst of energy, and then it simply traveled, uninterrupted, silent, alone, through the enormous cold emptiness between stars, for years, for centuries, for millennia, depending on which star you happen to be looking at, never slowing, never resting, carrying nothing but itself across a gulf so large that the ordinary units we use for distance, miles, kilometers, stop being useful at all, and astronomers switch instead to measuring in light years the distance. Light itself covers in a full year of uninterrupted travel. And after all that time, after all that distance, that particular beam's entire sole purpose, if it's fair to talk about purpose at all, turns out to be landing, gently, harmlessly, on the back of your eye, tonight, in this room, completing a journey that began before you had a name, before this house existed, before, in some cases, this entire country existed. Just sit with that for a second. Let it settle. Because here's the part that starts to feel strange once you actually think about it. When you look up and see a star, you're not seeing the star as it is. You're seeing the star as it was. You're looking into the past. Not metaphorically, literally. And the strange part isn't even that. The strange part is that this isn't some special exception for stars, some weird astronomy trick. It's true for everything. It's true for the wall across the room. It's true for the person lying next to you. If there's someone lying next to you, the light bouncing off their face and reaching your eyes took a tiny, tiny sliver of time to cross that gap. You're always looking very slightly into the past. Nobody notices, because at human scale the delays are so small they don't matter, a few billionths of a second, nothing your brain could ever register. But the principle is real. It never turns off. It's running right now, in this room, in this exact moment, however many light nanoseconds away your nearest wall happens to be. Here's a version of this same idea, scaled down to something almost embarrassingly ordinary, just to show you it's not confined to spaceships and distant stars. If you've ever made a video call to someone on the other side of the planet and noticed that tiny, awkward lag, the little half-second delay where your words arrive a beat later than you spoke them, that delay is a small, everyday cousin of exactly the same principle we're circling around tonight. The signal has to physically travel, bouncing off satellites or racing through undersea cables, and that travel takes time, a small but real and unavoidable amount of time, no matter how good the technology gets. Engineers can shrink that delay, but they can never make it zero, because nothing, not even the fastest signal humans can produce, escapes the basic fact that information has to cross a distance, and crossing a distance costs time. It's a small, mildly annoying inconvenience in everyday life. Scaled up to the distance between stars, that same small inconvenience becomes the entire reason the night sky is a patchwork of different pasts rather than a single shared present. And once you accept that, a door opens. Because it means that now, the thing that feels like the most solid, obvious, unquestionable fact in the universe, this very instant you're in, isn't quite what it seems. Tonight we're going to walk through this. Slowly. Not as a lecture. Not as something you need to follow closely or remember in the morning. Think of it more like a long, unhurried walk through the strangest, most fundamental layer of reality there is. If you drift off partway through, that's completely fine. The ideas will still be there. Nothing here requires you to stay sharp or take notes. You can let your grip on it loosen exactly the way you're letting your grip on the day loosen. Here's the shape of where we're headed. Time and space, which feel like two totally different things, one you live inside and one you move through, turn out not to be separate at all. They're two shadows of one deeper object that physicists call spacetime. And once you accept that they're stitched together, a whole cascade of things that sound like riddles, or contradictions, or magician's tricks, stop being wordplay and start being literal, sober descriptions of how reality is actually built. There's no universal now shared by the whole universe. Nothing can go faster than light, except space itself, which does it constantly, all the time, without breaking a single rule. Gravity isn't really a force, not in the way a shove or a pull is a force. A black hole isn't a hole. The universe has no center and no edge. And the Big Bang did not happen at a point, somewhere out there, the way an explosion happens somewhere in a room. One at a time, slowly, we'll take each of these and let it stop feeling like a contradiction and start feeling like just how things are. Let's start with the easiest one, the one about now. Picture two people. Call them whatever you like. It doesn't matter. They're just placeholders. One of them is standing still on a train platform. The other is sitting on a train, moving past the platform at a good, steady speed, nothing dramatic, just a normal train. And right in the middle of the train car, there's a little light, and it flashes once, sending light out in both directions at the same time, toward the front of the car and toward the back of the car equally. Now ask a simple question. Does the light hit the front wall and the back wall at the same time? If you're the person sitting on the train, the answer is obviously yes. The light left the middle, the walls are equal distances away. Of course it arrives at both walls at once. Nothing strange there. But if you're the person standing on the platform, watching the train go by, something different is happening. As far as you're concerned, the back wall of the train car is moving toward the point where the light flashed, chasing after that spot where the light started, and the front wall is moving away from it, retreating. So the light doesn't have to travel as far to catch the back wall, because the back wall is coming to meet it, and it has to travel a little farther to catch the front wall, because the front wall is running away from it. Which means, from your vantage point on the platform, the light hits the back wall slightly before it hits the front wall. Now here's the part that used to break people's brains, and honestly it should. Both of these people are right. Not right from their own perspective in some soft, everybody gets a trophy way. Right in the full, literal, physical sense. There is no hidden fact of the matter about which wall the light really hit first. The order genuinely depends on how you're moving relative to the flash. One observer's at the same time is another observer's one after the other, and neither of them is making an error, and neither of them has a better vantage point that would let them settle it. There is no umpire standing outside the universe who could check the replay and tell you the real answer, because there is no real answer beyond what each observer measures. This is what physicists mean by the relativity of simultaneity. Simultaneity, meaning things happening at the same time, turns out not to be one fixed, universal fact. It's relative. It depends on your motion. Let that settle for a second. Two events, either both happening together or one before the other, and which one is true depends on who's watching and how fast they're moving. Here's another version of the same idea, since it's worth turning over from more than one angle before we move on, and this one comes closer to how it was first described. Imagine two bolts of lightning striking, one at the front of a very long train and one at the back, and imagine, just for the sake of the experiment, that they strike in such a way that a person standing exactly halfway between the two strike points, out on the embankment beside the tracks, sees both flashes of light arrive at exactly the same instant. That observer, quite reasonably, concludes the two lightning strikes happened simultaneously. Now imagine a second person, sitting exactly in the middle of the train itself, moving past that embankment observer at the moment the lightning strikes. Because the train is moving forward, that second observer is rushing toward the front strike's light and pulling away from the back strike's light, and so they receive the front flash slightly before the back flash. From their point of view, the strike at the front of the train happened first. Both observers did everything correctly. Neither made a measurement error. They simply disagree, cleanly and permanently, about which lightning bolt struck first, and there is no further experiment either of them could run that would settle who's really right, because there genuinely isn't a deeper, hidden fact underneath their disagreement waiting to be uncovered. The order of distant events depends on your motion, full stop, and once you've turned this idea over twice, once with the flashlight in the train car, and once with lightning striking its two ends, it tends to stop feeling like a trick of language and start feeling like something you can almost, quietly, feel to be true. This is why a sentence like right now, on a distant star, something is happening doesn't actually mean anything precise. It sounds like it should. It sounds like the most natural sentence in the world. But right now for you and right now for a place trillions of miles away isn't a single, sharp, shared instant. There isn't a cosmic clock ticking the same universal beat for everyone everywhere, a master now that the whole universe is synchronized to. Every observer carries their own version of now, and those versions only line up neatly for things that are close by and moving slowly relative to each other, which is why you never notice this in ordinary life. Your now and the now of the chair across the room and the now of the person next to you. Those all line up close enough that the tiny discrepancies never surface. But stretch the distances out, speed the motion up, and the discrepancies stop being tiny. They become the whole story. So when you look up at the sky and you see a scattering of stars, you're not looking at a single frozen moment of the universe as it is right now. You're looking at a patchwork. Some of that light left its source 4 years ago. Some of it left 4,000 years ago. Some of it left before the pyramids were built. You're looking at many different pasts all layered on top of each other, arriving together, landing on your eyes in the same instant even though they started their journeys at wildly different points in time. The night sky isn't a snapshot. It's more like a stack of postcards, each one mailed from a different year, all delivered on the same evening. Let that image sit there for a moment. A stack of postcards, each mailed from a different year, all arriving tonight. And here's the thing worth carrying forward, because we'll come back to this starlight a few more times tonight. It's not just decoration. It's the whole clue. The fact that light takes time to travel, and that nothing can travel faster than it, and that different observers slice up time differently, depending on how they're moving. All of it traces back to this one starting point. Once you really absorb that there's no universal now, the rest of the confusions tonight aren't separate mysteries. They're just this same idea, worn into different shapes. Here's a way to feel the weight of this a little more before we move on. Imagine two twins. One of them stays home, living an ordinary life, growing older at the ordinary rate. The other twin climbs into a spaceship and travels away at an enormous fraction of the speed of light, out toward some distant star, and then turns around and comes back. When the traveling twin steps out of the ship, they're younger than the twin who stayed behind. Not because time played a trick on their body, not because the ship somehow preserved them, like a jar in a fridge, because they genuinely experienced less time. Fewer heartbeats, fewer thoughts, fewer days, measured honestly, by a clock that was running correctly and honestly the entire trip. People sometimes try to wriggle out of this by saying it's just a paradox, that from the traveling twin's point of view, it's the stay-at-home twin who was moving, so shouldn't the stay-at-home twin be the younger one instead? It's a fair question, and it's the reason this thought experiment is usually called the twin paradox, though it isn't really a paradox at all once you look closely. The two twins are not in symmetric situations. The one who stays home just sits there, moving in a straight line through space-time the whole time, or not moving at all, however you want to think about it. The one who travels has to accelerate, to turn around partway through the trip, to change direction, and that acceleration is a real, physical, measurable thing, felt as a push against the back of the seat, not just a matter of perspective. That asymmetry, the fact that one twin turns around and one doesn't, is what breaks the tie and settles, unambiguously, which twin actually ages less. It isn't a matter of opinion. If you ran the trip for real, with real clocks, the traveling twin would step off the ship and look at a calendar and find fewer days had passed for them than for their sibling. The evidence would be right there in their own body, in their own memories, an honest, physical record of less time having gone by. You might wonder if any of this actually shows up outside of thought experiments, and it does, constantly, quietly, all around you, even if you've never noticed it. High up in the atmosphere, cosmic rays slam into air molecules and produce tiny short-lived particles called muons, and those muons are moving toward the ground at close to the speed of light. Left alone, sitting still, a muon only survives for a couple of millionths of a second before decaying into something else, nowhere near long enough to fall all the way down through the atmosphere to reach a detector on the ground. And yet detectors on the ground pick up huge numbers of them, arriving intact, having made the trip. From our point of view, standing still on the ground, watching those muons streak downward at nearly light speed. Their internal clocks are running so much slower than ours that their few millionths of a second lifespan stretches out just long enough for them to survive the whole fall. Time dilation, playing out thousands of times a second in the air above your head, whether or not anyone happens to be watching for it. There's a subtlety worth mentioning here too, since it deepens this same idea rather than complicating it. When astronomers say a star or galaxy is a certain number of light years away, they're really describing how long its light took to reach us, not necessarily where that object actually sits right now. In this present moment, whatever right now ends up meaning for something that far away. Because space itself has been quietly stretching the entire time that light was in transit, the source of an old, distant beam of starlight is typically sitting even farther away today than it was when the light first set out, sometimes dramatically farther, the space between here and there having continued expanding for the whole duration of that light's long crossing. So even the seemingly simple question of how far away is that star turns out to have more than one honest answer, depending on whether you mean how far the light traveled, or how far the source has drifted since, or how far it sits at this very instant. A question that circles right back to the same tangle about now not being a single, simple, shared idea across the universe. So let's widen out a little. If now isn't universal, what about speed? What about motion itself? Because that's where things get even stranger, and it's where most people's intuition really starts to fight back. Here's a question. If you're standing still and you throw a ball forward at, let's say, 20 miles an hour, and I'm standing still watching you, I'll measure that ball moving at 20 miles an hour. Simple. But now imagine you're on a train moving forward at 60 miles an hour, and you throw that same ball forward at 20 miles an hour relative to yourself. I'm standing on the platform watching the train go by. How fast do I see the ball moving? Common sense says you just add the speeds together. 60 plus 20, 80 miles an hour. And for balls and trains and basically everything you've ever experienced directly, that's true. Or at least true enough that you'd never notice the tiny error. But now do the same experiment with light instead of a ball. You're on that train, and instead of throwing a ball, you switch on a flashlight, pointed forward. The light leaves the flashlight at the speed of light. Common sense says I, standing on the platform, should measure that light moving at the speed of light plus the speed of the train. Faster than light speed alone. That is not what happens. I measure the light moving at exactly the speed of light. Not the speed of light plus 60 miles an hour. Just the speed of light. Full stop. And if you, on the train, measure your own flashlight's beam, you also measure it moving at exactly the speed of light. Not a different number because you're moving. The exact same number. This was one of the strangest experimental results in the history of physics, and it took a teenager's daydream to make sense of it. Around 1895, a 16-year-old boy who'd just dropped out of a school he hated asked himself a simple question. What would it look like to ride alongside a beam of light, moving exactly as fast as it, keeping pace with it the way you might keep pace with a friend on a bike? Would the light look frozen, like a wave that stopped moving, a still photograph of an ocean swell that never breaks? And if so, what would that even mean? Because a frozen light wave shouldn't be possible under any of the rules of physics people knew at the time. That boy grew up to be Einstein, and that question sat with him for a decade before it cracked open into something enormous. The resolution turns out to be almost absurdly elegant once you see it, though it cost you something to get there. It cost you the assumption that time ticks at the same rate for everyone. If the speed of light has to come out the same for every observer, no matter how they're moving, then something else has to give. And what gives is time itself and space itself, not the speed, the measuring sticks. Here's a way to picture it. Imagine a clock built out of a single beam of light bouncing between two mirrors, one on the floor, one on the ceiling, a fixed distance apart. Each bounce, floor to ceiling and back, counts as one tick. If you're holding this light clock and standing still, the light just goes straight up and straight down, over and over. Tick, tick, tick. Now imagine you're holding that same light clock, but you're on a train moving forward. From your own point of view, nothing changes. The light still just goes straight up and down. Tick, 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 same as before. But from my point of view, standing on the platform watching your train go by, I don't see the light going straight up and down. I see it going up and forward, then down and forward, tracing out a zigzag, a longer diagonal path. Because the whole clock is moving forward while the light bounces. The light has to cover that longer, diagonal distance. And since the speed of light can't change no matter who's watching, covering a longer distance means it takes a longer time to complete each tick. Which means, from my vantage point on the platform, your clock is ticking slower than mine. This is time dilation. And here's the part that used to feel to me like the sky opening up when I first properly understood it. It isn't a trick of appearance. It isn't an optical illusion, a thing that only looks slower because of some quirk of how light reaches your eyes. Your clock actually runs slower, according to me, in a way that's every bit as real and physical as the clock ticking normally according to you. Both of you are correct. Time itself, the actual rate at which moments pass, depends on how you're moving relative to whoever's doing the measuring. And it isn't only clocks. Anything that measures time is affected the same way, because time dilation isn't a property of clocks specifically, it's a property of time. A person moving fast relative to you ages slightly slower, according to you. Their heartbeat, their thoughts, the chemical reactions in their cells, all of it, slowed down by the same factor as their clock, because there's nothing special about clocks. They're just one convenient way of tracking a much deeper thing that's happening to time itself. There's a matching effect for space, called length contraction, and it comes from exactly the same root. Moving objects measure shorter, in the direction of their motion, according to someone watching them go by. Not squashed like a cartoon, not physically crushed, just measured shorter, the same way their clock measures slower. Both effects flowing out of that one strange, stubborn fact that the speed of light refuses to change no matter who's chasing it or fleeing from it. There's a related puzzle worth sitting with for a moment, because it's the direct descendant of that ball and train question from a minute ago. If you're on a ship moving at, say, 3/4 the speed of light, and you fire a smaller probe forward at 3/4 the speed of light relative to the ship, ordinary addition would suggest the probe is now moving at 1.5 times the speed of light relative to someone watching from outside. That can't happen, and it doesn't. When you do the actual math, using the real rule for combining velocities rather than simple addition, the two speeds combine to something just under the speed of light, close to it, but never quite reaching it, let alone passing it. It's as though the universe is built in a kind of speed limit that gently refuses to let velocities stack all the way up to or past light speed, no matter how many times you try to add another push. Add speed to something already moving fast, and each additional push buys you less and less extra speed, the closer you get to the limit, the same way it might take you an ever-shrinking amount of ground to cover half the remaining distance to a doorway, without ever technically stepping through it. This is one more way of saying the same underlying thing. Space and time are stitchier than they feel, on constant alert to make sure the speed of light stays the one fixed, uncrossable finish line, no matter how creatively you try to sneak up on it. And length contraction, the shrinking of a moving object's measured length, has its own small real-world footprint too, tucked away in particle accelerators, machines built specifically to fling particles around at speeds close to light. Engineers designing these machines have to account for the fact that a fast-moving particle experiences the accelerator's tunnel as shorter than someone standing still beside it would measure it, and the maintaining of that consistency, length contracting exactly enough while time dilates exactly enough, is part of why the theory has been tested to such an extraordinary degree of precision without a single discrepancy ever turning up. It isn't a hypothesis anymore, hanging out there and proven. It's closer to a load-bearing assumption baked into some of the most delicate machinery humans have ever built. There's a deeper reason the speed of light matters so much, beyond just being a fast number, and it's worth understanding, because it ties directly back to that business about simultaneity from earlier. The speed of light isn't just a speed limit for objects, it's a speed limit for cause and effect themselves, for the ability of anything happening in one place to influence anything happening somewhere else. If you flip a switch here, the absolute earliest that switch could possibly affect something a certain distance away is limited by how long it takes light to cover that distance, no matter what technology or trick you might imagine using to send the signal faster. This carves the universe, at every single moment, into a kind of structure physicists call a light cone, an ever-widening zone of everything a given event could possibly have influenced, and a separate, ever-widening zone of everything that could possibly have influenced it, with a vast, unreachable region in between that's neither cause nor effect relative to that particular moment, simply because there hasn't been enough time for light, let alone anything slower, to bridge the gap. That murky, unreachable middle region is exactly where the relativity of simultaneity does its strange work, Because for events sitting outside each other's light cones, there is no fact of the matter, independent of an observer's motion, about which one happened first. It isn't that we don't know yet. It's that the question of order for those particular events simply doesn't have a single answer built into the universe, the same way the light hitting the front and back walls of that train car didn't have a single universal answer either. Causality itself, the whole tidy notion of causes coming before effects, only holds together cleanly within these cones. And it's precisely because the speed of light can't be exceeded that the whole structure manages to stay consistent for absolutely everyone, no matter how they're moving. There's a playful, slightly mind-bending puzzle built on length contraction that's worth turning over, mostly because it shows just how far this rabbit hole goes once you follow it honestly. Imagine a ladder, and a barn exactly the same length as that ladder when both are sitting still. Now imagine running that ladder toward the barn at a good fraction of light speed. According to someone standing still beside the barn, the moving ladder is length contracted, shorter than the barn, so for a brief instant, the whole ladder actually fits inside, with both barn doors able to close around it simultaneously. But according to the person carrying the ladder, they're the ones standing still, and it's the barn that's rushing toward them, contracted, shorter than the ladder, meaning the ladder could never possibly fit inside with both doors closed at once. Both descriptions are correct, simultaneously, which sounds like an outright contradiction until you remember the very first thing we talked about tonight, the relativity of simultaneity. The two observers simply disagree about whether the closing of the front door and the closing of the back door happen at the same moment. The barn observer sees both doors closing together, briefly, with the ladder fully enclosed. The ladder observer sees the doors closing at different times, never both shut while the ladder is inside. Neither is wrong. There's no ladder secretly bending or breaking. It's simply one more case where two honest, careful observers, moving differently, disagree cleanly about the order and timing of distant events, and both walk away with a perfectly consistent, perfectly correct account of what happened. Time dilation and length contraction sound like two separate weird tricks, but they're really one geometric fact wearing two different outfits. Space and time trade off against each other to keep the speed of light constant for everybody. That's the whole secret. Once you see it that way, it stops feeling like two arbitrary rules bolted onto the universe and starts feeling like a single, almost inevitable consequence of one deeper structure. Before Einstein, there was a whole tangle of confused experiments trying to make sense of exactly this. Physicists at the time assumed light had to travel through some invisible, undetectable medium filling all of space, something they called the ether, the same way sound needs air to travel through. And if the Earth was moving through this ether as it orbited the Sun, then light should travel at different measured speeds depending on which direction you shone it. Faster if you were measuring along the direction of Earth's motion through the ether, slower against it. The same way sound from a source ahead of you seems to reach you differently than sound from behind, if you're moving through still air yourself. Two researchers built an extraordinarily sensitive piece of equipment specifically designed to catch this difference, splitting a beam of light into two perpendicular paths and looking for the tiniest mismatch in how long each path took. They expected to find it easily. Instead, they found nothing. No difference at all, no matter which direction they pointed the apparatus, no matter what time of year they tried it, as the Earth swept through different parts of its orbit. It was one of the most famous null results in the history of science, an experiment that worked perfectly but found nothing where something was confidently expected, and for years it sat there as an open, nagging embarrassment, until Einstein's insight explained exactly why it had to come out that way. There was no ether to detect, because the speed of light doesn't depend on your motion relative to anything at all. It's just constant, for everyone, always, which is precisely the strange, stubborn fact this whole section has been trying to help you feel from the inside. There's one more consequence of all this worth sitting with, because it might be the single most famous equation to ever come out of physics, even though most people who can quote it couldn't tell you where it comes from. If space and time trade off against each other to keep the speed of light constant, it turns out mass and energy have to trade off against each other too, in an equally intimate way. Mass, in this picture, isn't some separate, unrelated property that objects just happen to have. It's a form of energy, an extremely concentrated, tightly packed form of it, And the exact rate of exchange between the two is set by the speed of light, squared, an enormous number, which is why converting even a tiny amount of mass into pure energy releases such a staggering quantity of it. This is the entire reason a small amount of nuclear fuel can power a city, or why the sun can keep shining steadily for billions of years, slowly converting a portion of its own mass into the light and warmth that eventually, after an 8-minute journey across 93 million miles of empty space, warms the side of your face on an ordinary afternoon. Mass and energy were never really two different things to begin with. They're the same underlying stuff, wearing two different outfits, in exactly the same spirit as time and space themselves. This also explains something that got mentioned early on but never quite unpacked: why nothing with mass can ever actually reach the speed of light itself, no matter how much energy you throw at it. As an object with mass moves faster and faster, closer and closer to light speed, it takes more and more energy to squeeze out each additional small increase in speed, the returns shrinking sharply the closer you get to the limit. Getting a massive object all the way to light speed, not close to it, but exactly at it, would require an infinite amount of energy, which simply isn't available anywhere in the universe, not in any star, not in any collider, not anywhere. Light itself gets away with moving at that speed only because it has no mass at all, nothing to accelerate in the ordinary sense, no resistance building up as its speed increases, since the whole troublesome buildup of required energy only applies to things that have mass to begin with. It isn't an arbitrary rule forbidding massive objects from trying. It's a genuine, physical wall, the energy cost climbing without any ceiling as you approach the limit, ensuring that light speed remains the one boundary nothing with mass can ever quite touch. There's a natural question that comes up at this point, and it's a good one. Doesn't that break the rule immediately? It doesn't, and the reason is one of the more beautiful distinctions in all of this. The speed limit applies to things moving through space. It does not apply to space itself expanding. Imagine a loaf of raisin bread rising in the oven. Every raisin sees every other raisin moving away from it, and the raisins that start out farther apart end up moving apart faster, purely because there's more dough between them, expanding. No individual raisin is racing through the dough at some tremendous speed. The dough itself, the space between them, is stretching. Nothing local is breaking any speed limit. It's just that when you add up enough stretching space over a long enough distance, the total rate of separation can exceed the speed of light, without any single thing anywhere actually moving faster than light relative to its own immediate surroundings. That's the difference between moving through space and space itself stretching, and it's a distinction that resolves and not a lot of people get stuck on. The speed of light limits motion within space. It says nothing about the growth of space itself, because space isn't a thing moving through space. It's the stage, expanding. Let's pause here and come back, just for a moment, to that starlight, since we're due for one of these little check-ins. All of this, the relativity of simultaneity, the constant speed of light, time dilation, length contraction, the stretching of space itself, all of it is baked into the light that's traveling toward you right now from somewhere impossibly far away, carrying an old past toward your eyes, on a night when space itself has been quietly expanding the entire time that light has been in transit, so that by the time it reaches you, the source that sent it is actually farther away than it was when the light first left. The light is a message from a place that, by the time you read the message, doesn't exist anymore in the same configuration. Let that settle. There's no need to hold on to it tightly. Just let it drift through. Now let's turn to gravity, because this is where things stop being about speed and start being about shape. Most of us grow up thinking of gravity as a force, something like a rope pulling you toward the ground, or a magnet pulling metal toward it. That picture works fine for everyday purposes, dropping a cup, throwing a ball, walking without floating away. But it isn't actually what gravity is, and the person who figured that out did it with one of the simplest thought experiments in the history of science. Imagine you're standing in a windowless elevator, and you have no way to look outside. Now imagine two different scenarios. In the first one, the elevator is sitting on the surface of the earth, and you feel your normal weight pressing your feet into the floor. In the second scenario, the elevator has been taken far out into deep space, away from any planet, any gravity at all, but it's being pulled upward by a cable, accelerating steadily, at exactly the same rate as Earth's gravity would produce. Here's the question. From inside that elevator, with no windows, is there any experiment you could run, any measurement you could take, that would let you tell which situation you're in? Standing on a planet, feeling gravity, or being accelerated through empty space, feeling the floor push up against you? The answer, astonishingly, is no. There is no experiment. Every ball you drop falls the same way. Every measurement of weight comes out the same. Standing still in a gravitational field and being accelerated through empty space are, as far as anything happening inside that elevator can tell, exactly, perfectly identical. This is called the equivalence principle, and it was the seed of an idea that grew into general relativity. If gravity and acceleration are locally indistinguishable, maybe gravity isn't a separate force at all. Maybe it's a byproduct of something else, and that something else turns out to be the shape of space-time itself. There's a flip side to that elevator experiment that makes the whole idea click even harder into place. Imagine, instead, that the elevator's cable has simply snapped, and it's now in complete free fall, plummeting down its shaft. Everyone's instinct says this should feel like the most extreme, most terrifying version of gravity imaginable. But it isn't. Anyone standing inside that free-falling elevator would feel weightless. Completely weightless. Nothing pressing against the floor, nothing pulling at their stomach in any lasting way. Just calm, floating stillness, right up until the moment the shaft ends. That's exactly what astronauts experience aboard a space station. And it surprises people to learn that they aren't weightless because they've escaped Earth's gravity. At the altitude of the space station, gravity is only slightly weaker than it is down here. They're weightless because they, and the station around them, are continuously falling, all the time, curving around the planet in what amounts to a very long, very graceful fall that keeps missing the ground because the Earth's surface curves away beneath them just as fast as they fall toward it. An orbit isn't an escape from gravity. It's a fall that never lands. And free fall itself, whether it's an elevator with a snapped cable or a space station circling the planet, isn't a special extra force acting on you. It's the absence of anything acting on you at all, the closest thing to true, unforced motion available in a universe where mass is always around, bending the paths that everything else naturally wants to take. Here's the picture that helps most people. Imagine a stretched rubber sheet, flat and taut. Now put a heavy bowling ball in the middle of it. The sheet dips down around the ball, curving inward. Now roll a marble across the sheet, off to one side. The marble doesn't move in a straight line anymore, because the sheet beneath it isn't flat anymore. It curves toward the bowling ball, following the dip in the sheet, and depending on its speed it might spiral in, or loop around, or swing past on a curved path. From a distance, it looks exactly like the marble is being pulled toward the bowling ball by some invisible force. But there's no force. There's no rope, no pull. There's just a marble moving in the straightest possible line through space that has been bent. That's gravity. Mass and energy bend the shape of space-time around them. And everything else, planets, light, you standing on the surface of the Earth right now, is just moving in the straightest possible line through that bent shape. What feels like a pull downward is actually you following curved space, the most natural, straight as possible path available to you through a region of space-time that Earth has warped. Gravity isn't a force reaching out and grabbing things. It's geometry. It's curvature. It's the shape of the room you're standing in, at a scale too vast and too subtle for your senses to notice directly, though your body feels the consequence of it every single moment, right now, as you lie there, held gently against whatever surface is beneath you. This picture, once you have it, makes black holes make a lot more sense. A black hole isn't a hole in the ordinary sense, a gap, or an absence. It's the opposite. It's an extreme concentration, so much mass packed into so small a space that the curvature of space-time around it becomes severe enough that, past a certain boundary called the event horizon, the straightest possible path for anything, even light, curves back inward, toward the center, with no way out. It isn't that light gets pulled back by some overwhelming force. It's that space itself is bent so sharply that there is no direction you could travel, no straight line available to you, that leads away. Every path, no matter which way you point, leads further in. That's why nothing escapes, not because it's being restrained, but because a way has stopped existing as an option. The geometry itself has closed that door. This also finally explains something that puzzled people for a very long time before Einstein came along, which is why planets orbit in smooth, repeating ellipses instead of, say, spiraling straight into the sun or flying off in a straight line. Under the old picture of gravity as an invisible pulling force reaching across empty space, it always felt slightly like magic, an attraction leaping across a gap with nothing in between to carry it. Under the curved space-time picture, there's no leap required at all. The sun's mass simply dents the space around it, the way the bowling ball dents the rubber sheet, and a planet orbiting nearby isn't being reeled in by an invisible line. It's simply coasting, in as straight a line as the local geometry allows, along a dent that happens to curve back on itself in a stable, repeating loop, the same way a marble rolled around the inside rim of a large bowl will keep circling smoothly, not because anything is grabbing it, but because the shape of the bowl itself keeps bending its path back inward. Gravity, once you see it this way, stops looking like an exception to how motion normally works, and starts looking like the most natural kind of motion there is. Once you account honestly for the actual shape of the room everything is moving through. There's a strange, almost dizzying twist to how time behaves near that boundary, and it's worth sitting with slowly rather than rushing past. If you imagine watching a friend fall toward a black hole from a safe distance, you would never actually see them cross the event horizon. As they fell closer and closer, the curvature of space-time around them would stretch their light more and more, and their clock, as you watched it through a telescope, would appear to tick slower and slower, their fall appearing to gradually freeze, fading and reddening, taking what looks from the outside like forever to actually reach that final boundary. But from your friend's own point of view, nothing dramatic happens at the horizon at all. They'd sail right through it, on schedule, according to their own watch, feeling nothing unusual in that instant, even though from your vantage point, it would look like they never quite got there. Two honest observers, two completely different, equally valid accounts of the same fall, one seeing an ending, one seeing a smooth continuation, and neither of them wrong, in the same spirit as those two people on the train platform from earlier tonight, just stretched now to an extreme almost too strange to picture comfortably. There's also a much more physically brutal effect worth knowing about, called spaghettification, and it's exactly as unpleasant as the name suggests. Near a black hole, the curvature of space-time changes so sharply over short distances that the pull on the near side of an object, a foot, say, closer to the horizon than the far side, can become dramatically stronger than the pull on the far side. That difference stretches anything falling in, elongating it along the direction of the fall while squeezing it from the sides, the way pulling on both ends of a piece of dough stretches and thins it in the middle. For small black holes, this happens violently, long before anything reaches the horizon. For truly enormous black holes, the kind found at the centers of galaxies, the curvature changes so gradually that something falling in might cross the horizon without being torn apart at all, at least not right away, which is its own kind of unsettling thought, drifting past a point of no return so smoothly you might not even notice you'd crossed it. And fully black isn't quite right either. Black holes glow, faintly, through a subtle quantum effect near the event horizon, and they can be surrounded by blazing disks of matter, spiraling in and heating up to extreme temperatures before it crosses that boundary. What's actually black is the region beyond the horizon itself, the true point of no return, the part where light cannot climb back out no matter how it tries. There's a beautiful, relatively recent confirmation of all of this that's worth knowing, since it happened within many people's own lifetimes rather than buried in old textbooks. If space-time really is a flexible, bendable fabric, then violent enough events, two black holes spiraling into each other and merging, say, should send actual ripples through it, waves of stretching and squeezing space itself, radiating outward in every direction like ripples spreading across a pond after a stone drops in. Einstein predicted these gravitational waves a century ago, but assumed they'd be far too faint ever to detect directly, a curiosity of the math rather than something anyone would actually measure. Decades later, engineers built an instrument sensitive enough to notice a stretching and squeezing of space itself smaller than 1/10,000th the width of a proton, using laser beams bounced down two long perpendicular tunnels, watching for the most infinitesimal mismatch between them. And in 2015, it worked. It picked up the unmistakable signature of two black holes, over 1 billion light-years away, having spiraled into each other and merged, over 1 billion years ago. The ripple from that ancient collision finally washing across the Earth and through that instrument, confirming, directly, physically, that space-time really does stretch and squeeze exactly the way the equations always said it should. It's a strange thing to sit with, that somewhere on this very planet, extraordinarily sensitive machinery is listening, quietly, for the aftershocks of cosmic collisions from unimaginably long ago and unimaginably far away, and every so often, it hears one. As for what's inside a black hole, this is a place where honesty matters more than false confidence. The math describing the interior points towards something called a singularity, a place where the curvature becomes infinite and the equations of general relativity stop giving sensible answers. But most physicists don't think this means there's literally a point of infinite density sitting there. They think it means the theory itself is breaking down, reaching the edge of where it applies. The same way a map that works beautifully across a whole country might simply have no markings at all once you reach the edge of the paper. The singularity isn't necessarily a real place. It's more likely a signpost, telling us we've reached the limits of what general relativity alone can describe, and that a deeper theory, one that properly includes quantum mechanics, would replace that infinite point with something else, something we don't yet fully understand. There's a lovely piece of historical evidence for all of this, one that predates satellites and space stations by more than a century. Astronomers had long noticed a small, stubborn anomaly in the orbit of Mercury, the planet closest to the Sun. Its orbit wasn't a perfectly repeating ellipse, the way Newton's older theory of gravity predicted. The whole orbit itself was slowly rotating, tracing out a very slight rosette pattern over time rather than a fixed, closed loop, drifting just slightly more than Newton's equations could account for, no matter how carefully astronomers tried to explain it away with unseen planets or measurement errors. Einstein's new picture of gravity as curved space-time, when applied to Mercury sitting deep in the Sun's strong gravitational curvature, predicted that exact leftover drift to a precision that stunned people at the time. It wasn't a picture invented to explain the anomaly after the fact. The theory was built from entirely different starting principles: the elevator, the equivalence principle, the geometry of curved space, and it happened to also perfectly resolve a puzzle that had been sitting unsolved in astronomy for decades. That kind of unplanned, precise agreement between a beautiful idea and a stubborn old data point is about as close as science ever gets to a moment of genuine vindication. This isn't only satellites, either. Decades ago, researchers ran a wonderfully direct, almost charmingly low-tech version of this test. They took extremely precise atomic clocks, the kind accurate enough to notice differences of billionths of a second, and flew some of them around the world on ordinary commercial airliners, while keeping an identical set of reference clocks sitting still on the ground. When the traveling clocks landed and were compared against the stationary ones, they showed a tiny but very real and very measurable difference, exactly matching what the combination of their speed and their altitude predicted they should show: a small blend of the motion-based time dilation from moving fast and the gravity-based time dilation from sitting slightly farther from the Earth's mass at cruising altitude. Both effects layered together and both confirmed on ordinary passenger jets, with clocks anyone could have carried in a briefcase. It's a strange thing to picture, that hidden somewhere in the cargo hold of an unremarkable flight, decades ago, was direct, physical proof that time itself doesn't move at one single, universal rate for everyone, quietly ticking a little differently mile by mile, the whole flight through. This effect is so real, and so precisely measurable now, that it shows up at almost absurdly small scales. Because gravity's curvature weakens with distance from a mass, and time runs at a very slightly different rate depending on how deep you are in that curvature, the top of your head, right now, lying there, is aging very, very slightly faster than your feet, simply because your head sits a few inches farther from the center of the Earth, in a marginally weaker dip in the curve. The difference is utterly imperceptible across a single lifetime, far too small for any bodily process to register, But modern atomic clocks are now sensitive enough to detect exactly this kind of height difference directly, clocks separated by no more than the height of a single stair step, showing a measurable difference in their ticking rate. It's a strange, almost funny thought to end on, that your own body, right now, is very gently, very slightly, experiencing time at two faintly different rates from head to toe, a small, quiet, physical reminder that the curvature we've been discussing isn't only out there, around planets and stars, but here too, in this very room, at the scale of your own resting body. There's one more strange wrinkle worth knowing about gravity's shape, because it shows that curvature isn't only about how much mass is present, but also about how that mass is moving. A spinning mass, it turns out, doesn't just curve spacetime the way a stationary one does. It also drags the surrounding spacetime around with it, slightly. The way a spoon stirred through honey doesn't just displace the honey directly beneath it, but pulls the honey around it into a gentle, swirling rotation too. This is called frame dragging, and it's been measured directly around the spinning Earth itself, using satellites carrying extraordinarily precise gyroscopes, sensitive enough to detect the almost unbelievably faint twist that our planet's rotation imparts on the spacetime surrounding it. The effect around the Earth is minuscule, a barely perceptible nudge, but around something far more massive and far more rapidly spinning, like certain black holes, frame dragging becomes dramatic, twisting the surrounding spacetime so severely that anything nearby is forced to orbit along with the rotation whether it wants to or not, unable to simply hover still. The way a leaf caught near a whirlpool can't simply sit motionless in the swirling water beside it. Spacetime, in other words, doesn't just bend. It can be stirred. Here's a grounding thought before we move on, and it's one of my favorites, because it isn't philosophy, it's already sitting in your pocket. Every time you use GPS on your phone, you are relying, quietly and invisibly, on the fact that gravity curves spacetime. The satellites broadcasting your position are farther from Earth's mass than you are, sitting in a region of weaker curvature, and so their clocks run at a very slightly different rate than clocks on the ground, a matter of millionths of a second per day. It sounds negligible. It isn't. If engineers didn't correct for that tiny mismatch, the errors would compound, and within about a day, GPS positioning would drift off by several miles. The blue dot on your phone map would slowly wander away from where you actually are, until it became useless. The fact that your phone can find you within a few feet is a small, daily, practical proof that the strange geometric picture of gravity we just walked through is not an abstraction. It is running, right now, quietly, in the software of a piece of hardware in a pocket, keeping cars from getting lost, and helping people find their way home. Let that settle. The most reality-bending stuff we've talked about tonight is also some of the most reliable, boring, load-bearing infrastructure in modern life. Now let's widen out even further, all the way out, to the beginning of everything, and to whether everything has an edge. Here's a phrase that gets used constantly, and it's almost always slightly wrong, or at least deeply misleading. The Big Bang. People picture an explosion, something going off at a particular point in space, flinging matter outward into a pre-existing emptiness, the way a firework detonates in the sky. That picture is natural, intuitive, and it isn't what happened. The Big Bang wasn't an explosion happening at a point within space. It was the beginning of space itself. There was no empty void sitting around waiting to be filled. Space itself, the very fabric that galaxies now sit within, began and has been expanding and stretching ever since, the same way that raisin bread dough was expanding earlier, except this expansion is the birth of the dough itself, not just its growth. Every point in the universe today was, in the earliest moments, part of an incredibly dense, incredibly hot state, and every point has been moving apart from every other point ever since, not because anything is flying through space away from a central point, but because space itself, everywhere, all at once, has been stretching. This means there is no location you could travel to that marks where the Big Bang happened, the way you could travel to the site of a historical battle. It happened everywhere, because everywhere is what came out of it. If you rewound the expansion of the universe like a film played backward, you wouldn't be zooming in on some far-off point in the sky. You'd be watching the space around you, right here, right now, shrink, along with the space everywhere else, until it all merged into that same incredibly dense beginning. The Big Bang didn't happen out there. In a sense, it happened right here too, along with everywhere else, because here is itself a product of that same original expansion. Here's a small, quiet piece of evidence for all of this that's been sitting around the universe this whole time. Faint and ancient and easy to miss unless you know to look for it. If space really did begin in an incredibly hot, dense state and has been expanding and cooling ever since, there should be a leftover afterglow, a faint bath of radiation filling the entire universe, stretched by billions of years of expansion down into very weak, very cold microwaves. And there is. It's called the cosmic microwave background, and it was discovered almost by accident, by two researchers trying to figure out why their radio antenna kept picking up a persistent, uniform hiss they couldn't get rid of, no matter which direction they pointed it or how carefully they cleaned pigeon droppings out of the equipment. That hiss turned out to be the oldest light in the universe, dating back to a time when everything was still an opaque, glowing fog, before atoms had even properly formed, stretched by nearly 14 billion years of expansion into the faint microwave hum that quietly fills every direction of the sky, including, right now, the empty space just outside your window. It's one of the most direct, physical confirmations that the universe really did begin in that hot, dense state, an actual, measurable fossil of the very beginning, rather than a story we've simply decided sounds plausible. And this reframes the classic question that trips almost everyone up eventually. What came before the Big Bang? It's a completely natural question to ask, and it might genuinely be a question that has no answer, not because we're too limited to find it, but because the question itself might not quite make sense. The way asking what's north of the North Pole doesn't quite make sense. North is a direction defined relative to the pole, and once you're standing at the pole itself, every direction you could possibly step is south. North simply runs out, not because there's a wall or a boundary there, but because the concept of north was never something layered independently on top of the Earth. It was always just a relationship, a direction defined by the geometry of the globe. And at the pole, that relationship has nowhere left to point. Time, in the same way people generally use the word, might be something that only exists because space-time itself exists, might be woven into the fabric of this universe rather than sitting on some separate, prior timeline waiting for the Big Bang to happen. If that's true, asking what happened before the Big Bang is a bit like asking what's north of the North Pole. Before, as a concept, might require a timeline for it to be measured against, and that timeline is part of what started at the beginning, not something that was already running while we waited for the universe to show up. This doesn't mean physicists have stopped asking the question. There are genuinely fascinating, speculative ideas out there about what might lie beneath or before our universe's beginning, but it does mean the ordinary, everyday sense of before might simply not apply. The way the compass needle spins uselessly once you're standing exactly on top of the pole. You've almost certainly felt a version of this effect yourself, in an entirely everyday setting, even if you never thought of it as related to the edge of the observable universe. Think of a train whistle as the train approaches you, then passes, then recedes down the track. While it's approaching, the pitch sounds higher, the sound waves bunched slightly closer together by the train's motion toward you. Once it's passed and is moving away, the pitch drops, the waves stretched slightly farther apart by the train's retreat. Nothing about the whistle itself changed. Only the motion relative to you changed, and that motion stretched or compressed the sound waves reaching your ears. Light does something similar. And the redshift from cosmic expansion is really just that same idea, playing out with light instead of sound, and with space itself doing the stretching rather than an object physically moving away through still air. The galaxies aren't necessarily rushing away from us the way a train rushes down a track. Mostly, it's the space between us and them quietly growing, stretching their light the same patient way a slowly inflating balloon would stretch a drawing made on its surface, longer and thinner, the farther the balloon expands. There's a neat, practical way astronomers actually read this stretched past directly out of starlight, rather than just inferring it. Because space itself has been expanding the whole time light from distant galaxies has been traveling toward us, that light gets stretched along with the space it's crossing, its wavelength pulled longer, shifted toward the red end of the spectrum, an effect fittingly called redshift. The farther away a galaxy is, Generally speaking, the longer its light has been traveling, the more space has expanded during that journey, and the more its light has been stretched and reddened by the time it reaches a telescope. Astronomers can measure that stretching precisely, and from it, read off both how far away a galaxy is and how long ago the light we're seeing actually left it. In a very real sense, telescopes aren't just looking outward into distance. They're looking backward into time, and the farther out they look, the further back they see, all the way toward that hot, dense, ancient fog whose leftover glow we mentioned a moment ago. Every deep-field image of thousands of faint, ancient galaxies is really a photograph of deep time as much as deep space, a single frame containing slices of the past stretching back billions of years, all layered together the same way the ordinary night sky layers together starlight of wildly different ages, just on a far grander and more dizzying scale. There's one more speculative thread worth pulling on gently before we move past the beginning entirely. In the earliest possible fraction of a second after the universe began, there's strong evidence for an extraordinarily brief, extraordinarily violent period called inflation, where space itself stretched by an almost incomprehensible factor in a sliver of time far shorter than anything you could consciously register, smoothing out the early universe and setting the stage for everything that came afterward, including the tiny seeds that would eventually grow into galaxies. What triggered inflation, and what, if anything, might have existed before or alongside it, remains genuinely open. Some physicists have floated the idea that inflation might not have been a single, one-time event, but something that continues even now, endlessly, in regions impossibly far beyond our observable horizon, spawning what would effectively be separate, disconnected universes, bubbling off from each other forever, with our own observable universe being just one bubble among an unknown, possibly unlimited number of others. This is often called the multiverse, and it's important to be honest about where it sits, scientifically. It isn't confirmed. It isn't even clearly testable with current technology, and some serious physicists consider it more of a mathematical curiosity than a genuine physical prediction. But it's a natural, well-motivated extension of ideas that do have solid evidence behind them. And it's one more example of how the honest frontier of physics right now involves questions this large, this strange, still sitting there, unresolved, waiting. All of this traces back to a discovery made less than 100 years ago, which is startlingly recent given how fundamental it now seems. For most of history, even into the early 20th century, the prevailing assumption was that the universe was static, fixed, eternal, existing the way it always had and always would, with nothing so dramatic as an expansion or a beginning. A patient astronomer, spending long nights measuring the light from faint, fuzzy patches in the sky that most people assumed were simply clouds of gas within our own galaxy, discovered two things that upended that assumption entirely. First, that many of those fuzzy patches were actually entire separate galaxies, unimaginably far beyond our own, each containing billions of stars in their own right. And second, that nearly all of them showed that same reddened, stretched light we talked about a moment ago, and that the farther away a galaxy sat, the more stretched its light appeared, in a clean, consistent pattern. The only sensible explanation was that space itself was expanding, carrying those galaxies apart from us and from each other, faster the farther away they already were. It was such an enormous shift in understanding that even the physicist whose own equations had predicted an expanding universe years earlier, before there was any observational evidence for it, had initially added an extra fudge factor to his own math specifically to force a static, unchanging result, assuming his equations simply had to be wrong, since surely the universe couldn't actually be expanding. He later called that decision one of the biggest blunders of his career, once the evidence came in showing the expansion had been sitting there in the math all along, waiting patiently to be believed. Here's a smaller, gentler puzzle that fits right alongside this one, and it's a genuinely old one, first properly puzzled over centuries ago. If the universe is enormous, maybe infinite, and it's been around for a very long time, filled with countless stars, then shouldn't the night sky be blazing bright everywhere you look? After all, if you look in literally any direction, eventually your line of sight should hit a star, somewhere, given enough distance and enough stars scattered through an old, dense universe. So why is the night sky dark rather than a wall of light? This is called Olber's paradox, and the resolution weaves together almost everything we've talked about tonight. The universe is not infinitely old. It has a finite age, meaning light from the most distant stars and galaxies simply hasn't had time to reach us yet, no matter how long we wait, because those regions are so unimaginably far away. And the universe has been expanding this whole time, stretching the light from distant sources, spreading its energy thinner and thinner, shifting it out of visible light and into wavelengths our eyes can't detect at all. So the night sky isn't dark because there's nothing out there. It's dark partly because the oldest light hasn't arrived yet, and partly because the light that has arrived from the most distant reaches has been stretched by the expansion of space into something invisible to our eyes. Darkness itself, it turns out, is evidence. It's telling you something specific and profound about the age and the expansion of everything around you, just by being dark instead of blazing. There's a particular puzzle that inflation was originally invented to solve, and it's a good one to sit with, because it shows how strange the universe's uniformity really is once you think about it carefully. Look at the leftover afterglow of the Big Bang in opposite directions of the sky, regions so far apart that, under ordinary expansion alone, light would never have had time to travel between them and let them settle into the same temperature, the same density, the same basic conditions. And yet they match, almost perfectly, to a precision that seems to demand some kind of shared history, some kind of contact early on to iron out the differences. This is called the horizon problem, and it's a genuine puzzle if you assume the universe simply expanded at an ordinary, steady pace the whole time. Inflation resolves it by proposing that all these now distant regions were once, briefly, close enough together to reach a shared equilibrium, before that extraordinarily brief burst of stretching flung them apart to their current. Vast separations faster than light could have kept them talking to each other afterward. It's a strange, almost paradoxical fix, using an episode of expansion faster than anything light could achieve to explain why regions that can no longer communicate still look like they once did. But it fits the data remarkably well, and it's one of the main reasons physicists take inflation seriously, even though the deepest mechanics of what triggered it remain an active, ongoing puzzle. There's a further wrinkle to the expansion itself, discovered only a few decades ago, that's worth knowing, because it changes the ending of this particular story. For a long time, physicists assumed the expansion of the universe had to be slowing down, the way a ball thrown into the air slows as gravity pulls back on it, since all that mass, all those galaxies, should be tugging on each other, gradually breaking the whole expansion. Astronomers set out to measure exactly how much the expansion was decelerating, using distant exploding stars as reference points, bright enough and predictable enough to act as reliable cosmic yardsticks. And what they found instead startled almost everyone involved. The expansion isn't slowing down. It's speeding up. Something is pushing galaxies apart faster and faster as time goes on. Some mysterious property of empty space itself that physicists have given the placeholder name dark energy, largely because nobody yet has a satisfying account of what it actually is, only very precise measurements of what it's doing. It seems to make up roughly 2/3 of everything in the universe by energy content, and it remains one of the largest open questions in all of physics, a genuinely humbling reminder that even now, after everything we've walked through tonight, most of what the universe is made of is still, honestly, a mystery. This brings us to a natural question about edges. If the universe is expanding, is there an edge to it, a boundary where the universe stops and something else, some kind of outside, begins? As far as anyone can tell, no. There's no edge, in the way a balloon's surface has no edge. Picture the surface of a balloon, just the surface, the two-dimensional skin of it, with dots drawn all over to represent galaxies. As you inflate the balloon, every dot moves away from every other dot, and there's no special dot at the center of the surface, and no edge anywhere on that surface where the dots stop. The whole surface is uniformly stretching everywhere at once, with no boundary and no privileged center. The universe seems to work something like that, though in 3 dimensions of space rather than the two-dimensional surface of a balloon, which makes it much harder to visualize but doesn't change the logic. No center, no edge, just uniform expansion happening everywhere, all at once. What we do have is something called the observable universe, and this is a genuinely different concept from an edge, even though people often confuse the two. The observable universe is a horizon, not a boundary. It marks the farthest distance light could have traveled to reach us in the roughly 14 billion years since the beginning. Beyond that horizon, there could be more universe. Almost certainly is more universe, stretching on, perhaps forever, but we can't see it, because light from that far away simply hasn't had time to arrive yet. It's a horizon in the same sense that the horizon on the ocean isn't the edge of the world. It's just the limit of how far you can see from where you're standing. Sail toward it, and it recedes ahead of you. Always the same distance away, not because the ocean is fleeing from you, but because the horizon was never a place, only a limit of sight. The observable universe works the same way. It's not a wall. It's just how far our light has reached us in the time available. Let's pause once more, back to the starlight, because it's carrying almost the entire weight of tonight's conversation. That light landing on you right now is old news from a young universe, arriving at the edge of what you can see, a literal horizon of time stretching back toward a beginning that didn't happen at a point, but happened everywhere, including right where you're lying now. Let that settle. There's nowhere you need to go with this thought. Just let it rest there. Now, for the final stretch tonight, let's go to the deepest layer, the place where even physicists start choosing their words very carefully. Here's a question that seems almost too simple to be interesting. Why does time seem to flow in one direction? Why can you remember yesterday, but not tomorrow? Why does an egg break when it falls, but never spontaneously reassemble itself from a puddle of yolk and shell fragments back onto the counter? It feels obvious, intuitively, that time has a direction, a clear arrow pointing from past to future, and that this arrow is one of the most basic facts about reality. Here's the strange part. Almost none of the fundamental laws of physics actually require this. If you watched a film of two billiard balls colliding and bouncing apart, and then watched the exact same film played backward, both versions would look perfectly consistent with the laws of motion. Nothing in the underlying physics says which direction is the real one. The equations don't care. Play them forward or backward, they work either way. So why does the world we actually experience only ever seem to run one direction? Why do eggs break, but never unbreak? The answer lies not in the fundamental laws themselves, but in probability, in something called entropy. Entropy, roughly speaking, is a measure of how many different ways the tiny particles inside something could be arranged while still looking the same from the outside. An intact egg has very few arrangements of its atoms that would count as an intact egg. It's a very specific, ordered structure. A broken egg splattered across the floor has an enormous number of possible arrangements of those same atoms that would all count as a broken mess, because a mess can be arranged so many more ways than an orderly structure can. So when the egg falls and breaks, it isn't being forced into a mess by some cosmic rule demanding one direction of time. It's simply moving from an arrangement with very few possible configurations toward one of the vastly, overwhelmingly larger number of possible messy configurations, because there are so many more ways to be broken than to be whole, and given enough interactions, the odds overwhelmingly favor drifting toward the more probable, Messier state. Here's a smaller, more portable version of the same idea, one you could actually try, if you ever wanted to, though there's no need to get up and do it right now. Take a brand new deck of cards, still in its perfect factory order, and shuffle it. Just once, thoroughly. The odds that shuffling would return the deck to that exact original order, or to any other single specific, meaningful order, are so vanishingly small that it effectively never happens, not in the whole history of anyone ever shuffling cards. Not because there's a rule against it. Every single arrangement of 52 cards is exactly as likely as every other single arrangement, including the perfect factory order. It's just that there is exactly one arrangement that counts as perfect factory order, and there are an almost incomprehensibly vast number of arrangements that count as shuffled and messy, so any random shuffle overwhelmingly lands you somewhere in that enormous messy category, not because the universe is steering you there, but because that's simply where nearly all the available options happen to sit. Entropy increasing isn't a mysterious force pushing things toward disorder. It's just what happens when you let something bounce around freely among a huge number of possible states. and only a tiny fraction of those states happen to look orderly to us. Stretch that idea out across the entire universe, over unimaginably long timescales, and you arrive at something physicists sometimes call the heat death of the universe, an extremely distant, extremely gradual future state where everything has spread out and settled into the most probable, most featureless configuration available, a thin, cold, uniform haze with no more usable energy differences left to do anything interesting with, no stars left to burn, no structures left to form, just a very long, very quiet stillness. It's an almost unimaginably far-off possibility, so distant in time that comparing it to the present age of the universe is like comparing a single grain of sand to a beach that stretches beyond the horizon. And it's not something that needs to sit heavily on you tonight. If anything, it's a strange kind of comfort, a reminder of just how much time, how much room, how much unfolding is still ahead, long before anything like that quiet ending would ever arrive. The arrow of time, then, isn't a fundamental law written into the fabric of physics the way the speed of light is. It's closer to a statistical tendency, an overwhelming likelihood, because the universe started out in an extraordinarily ordered, low-entropy state near the Big Bang, and has been drifting toward Messier, higher entropy arrangements ever since, and that steady drift toward mess is what you experience as time moving forward. Underneath, the actual laws of physics don't care about direction at all. It's the probabilities piling up in one direction, relentlessly, that give you the felt experience of time only ever moving one way. There's a deeper puzzle tucked inside all of this, one that even physicists find genuinely uncomfortable, and it's worth naming honestly rather than glossing over. If entropy naturally tends to increase, drifting toward mess, then the universe must have started out in an extremely special, extremely ordered, extremely low-entropy state near the Big Bang, dramatically more ordered than almost any state it could have started in. If you imagine all the possible ways a universe could have begun, why would the universe happen to start in such a wildly improbable, orderly condition, rather than in one of the vastly more numerous messy configurations available to it? This is sometimes called the past hypothesis, and honestly, nobody has a fully satisfying answer for it yet. It sits there, at the very root of why time has a direction at all, an assumption physics currently has to simply take as given, rather than something the deeper theories explain from first principles. It's one of the genuinely open frontiers, a reminder that even a story as sweeping as tonight's still bottoms out, eventually, in an honest shrug, in a place where the very best current understanding says, essentially, this appears to be how things were, without yet being able to say fully why. This leads to one of the strangest, most debated ideas in all of physics, something called the block universe. If the fundamental laws don't actually prefer a direction of time, some physicists take this seriously enough to suggest that maybe the past, present, and future all exist equally, all the time, the way different points along a road all exist simultaneously even though a traveler only experiences them one at a time, moving along the road. Under this view, your childhood isn't gone, exactly. It's just a region of space-time, sitting there, just as real as this present moment, the same way a city 1,000 miles away is not gone just because you aren't currently standing in it. And the future, under this view, isn't a blank slate waiting to be written. It's another region of the same block, already there, in the same sense that the past is there, just not a region you've reached yet in your own personal journey through it. This isn't universally accepted, and there are serious physicists who resist it or interpret it differently. But it's taken seriously enough, discussed carefully enough, that it's worth knowing it's out there as a genuine possibility. One of the stranger implications of taking relativity's blurring of past, present, and future completely at face value. This isn't universally accepted, and there are serious physicists who resist it or interpret it differently. But it's taken seriously enough, discussed carefully enough, that it's worth knowing it's out there as a genuine possibility. One of the stranger implications of taking relativity's blurring of past, present, and future completely at face value. If the block universe picture is right, or even close to right, it changes how you might think about memory itself. Memory feels, from the inside, like a window looking backward, a way of reaching into a past that no longer exists and pulling a little of it forward into the present. But under this view, Memory might be better described as more like a connection than a window, a physical link between one region of the block, where a particular experience is sitting permanently, unchangeably, in this region, where you happen to be right now, doing the remembering. The past isn't gone in the way a demolished building is gone. It's simply somewhere else along the block, not here, not now, but no less real for that. The same way a memory of a childhood bedroom doesn't require that bedroom to still exist in order for the memory to be pointing at something that was, once, genuinely and completely real. This can feel oddly comforting once it settles in properly. Nothing you've lived through has been erased. It's just no longer the region of the block you happen to be occupying. There's a question people naturally arrive at once they sit with the block universe for a while, and it deserves a brief, honest mention, even if it isn't fully resolvable tonight. If the future already exists, in the same sense the past does, sitting there as a fixed region of the block, does that mean everything that will ever happen is already somehow settled, decided, with no real room left for choice? This is a genuinely old philosophical question, far older than relativity itself, and relativity doesn't exactly settle it one way or the other. It mostly just gives the old question a sharper, more physical shape. Some philosophers argue that a fixed, existing future is perfectly compatible with meaningful choice, since your choices are still the very things that determine what that region of the block contains. In the same way, a completed novel still required an author to write each sentence, even though every page already exists between its covers once it's finished. Others find that picture cold or unsatisfying. Nobody has landed on an answer that fully closes the question. It's one more place where the physics hands you a strange, well-supported picture of reality and then quietly steps back, leaving the rest of the sorting out to the individual, in their own time, at their own pace, with no requirement to finish that sorting tonight. Let's touch, lightly, on one more piece, because it's worth knowing about even without diving deep into it tonight. There's a phenomenon called entanglement, where two particles can become linked in such a way that measuring a property of one instantly tells you something about the other, no matter how far apart they are, even if they're on opposite sides of the galaxy. This sounds, at first, like it should let you send a signal faster than light, breaking everything we talked about earlier. It doesn't, and the details of why are subtle, but the honest short version is that entanglement doesn't let you transmit usable information faster than light, even though it does connect distant particles in a way that still puzzles physicists today. Some researchers have gone even further and floated the speculative idea that space-time itself, the very fabric we've been describing all night, might not be fundamental at all, but might somehow emerge from networks of entanglement between more basic underlying pieces, the way temperature emerges from the jostling of countless molecules without any single molecule itself having a temperature. This is speculative, genuinely at the frontier, not settled science, but it's a sign of just how deep the strangeness goes, that even space-time itself, the stage on which everything else in tonight's conversation has played out, might turn out to be built from something even stranger underneath. There's one more layer beneath even that, worth mentioning gently before we let all of this go for the night. If space-time itself might emerge from something more fundamental, a natural question is whether space and time are smooth all the way down, infinitely divisible, or whether they come in some kind of smallest possible unit, a grain beneath which the very ideas of distance and duration stop making sense. There's a length scale physicists call the Planck length, unimaginably small, far smaller than an atom, far smaller than anything we have any hope of directly probing with current instruments, where many suspect the smooth, continuous picture of space-time we've been using all night might break down into something more like a foam, a shifting, uncertain, bubbling texture, rather than the calm, flat fabric the rubber sheet picture suggested earlier. Nobody knows this for certain. It's speculation sitting right at the edge of what physics can currently test, a place where the equations start hinting at something, but the experiments haven't caught up enough to say for sure. But it's a fitting place to end up, honestly, because it means that even the very stage on which stars form, and light travels, and clocks tick differently for people in motion, and black holes bend the paths of everything nearby, might itself be woven from something even stranger, still waiting to be properly understood by someone, someday, possibly not for a very long time yet. There's a strange, almost dizzying wrinkle to entanglement, one that took decades to nail down properly, worth mentioning even briefly. For a long time, some physicists, including Einstein himself, suspected entangled particles must simply carry some kind of hidden, pre-agreed instructions with them from the moment they became entangled, a bit like two gloves packed into separate boxes and sent to opposite ends of the world, so that opening one box and finding a left glove tells you instantly, but entirely unmysteriously, that the other box contains a right glove. No strange, instant connection required, just information that was quietly there all along, waiting to be revealed. A careful set of theoretical arguments, later tested directly in real laboratories, showed this simple explanation can't be the whole story. The particles genuinely do not carry fixed, hidden answers decided in advance. Something about their connection is more thoroughly linked than any hidden glove picture could account for, confirmed experimentally, repeatedly, in ways precise enough to rule out the tidy explanation almost everyone initially reached for, including some of the smartest people who ever lived. Exactly what that connection means, physically, remains genuinely debated. But it isn't a loophole, and it isn't a trick of statistics. It's one of the most carefully verified strange facts in all of physics. It's also worth pausing, gently, on something closer to home, since we've spent so long tonight taking apart the idea of a single universal now. Your own felt sense of the present moment, this specific instant you're in, reading or listening to these words, feels like the most vivid, most undeniable thing there is, more real, somehow, than the past or the future. Physics doesn't really explain why that feeling exists, why consciousness seems to ride along one particular slice of the block universe rather than experiencing all of it evenly, the way it seems to sit there in the equations. That gap between the deeply mathematical picture of a block where past and future are equally real, and the deeply personal experience of a present moment that feels singled out, special, the only one that's truly happening, is still an open question, sitting somewhere at the crossroads of physics and philosophy and the workings of the mind. Nobody has a tidy answer for it yet. It's one more thing that's fine to simply hold loosely, unresolved, as you drift. And here, honestly, is where I think it's best to leave it. Not with a tidy bow, not with every thread resolved, but with an honest acknowledgement that the math, in every case we've walked through tonight, works far better than intuition ever will. Your gut feelings about time and simultaneity and gravity and beginnings were built by evolution for a world of walking speeds and everyday distances, a world where none of these effects ever mattered enough to matter. It's not a failure of your mind that these ideas feel strange. It would be strange if they didn't. And it's perfectly fine to rest inside that gap, the space between what your intuition expects and what the equations actually say, rather than needing to fully close it before you can relax. So let's come back, gently, to where we started. That starlight, still arriving, still carrying its old message, still crossing that great stretched span of expanding space, has been the whole night's true subject. It began its journey long before this quiet room, long before this bed, long before you existed in anything like their current form, and it's arriving now, tonight, adding one more layer to that ancient stack of postcards mailed from 1,000 different years. And beneath you, right now, the mattress is holding you up not by pushing back against some mysterious pulling force from below, but because space-time itself is gently curved beneath you by the mass of the whole planet, and you are simply following the straightest possible path available to you through that curve, which happens, right now, to be resting still. The room around you, the walls, the ceiling, the person or the pet or the silence beside you, all of it sits inside the same fabric we've spent tonight trying to understand, quietly warping and stretching and ticking at its own slightly different rate, everywhere, all the time, without needing your attention or your understanding to keep working. You don't need to hold on to any of this. You don't need to remember the names or the details or even the shape of the argument. What can stay with you, if anything does, is simpler than all of that. The universe is built out of something far stranger and far more elegant than it appears to be from the inside of an ordinary day. And you don't have to solve it or fully grasp it or carry it forward into tomorrow to have spent a little while, tonight, genuinely closer to understanding it. Somewhere outside, if there's a window nearby, or even if there isn't, that same starlight is still arriving, indifferent to whether anyone happens to be looking, indifferent to whether it's understood or simply felt as a faint, distant point of light in a dark sky. It doesn't need you to know any of what we've talked about tonight in order to keep doing what it's always done, crossing that enormous, patient distance, landing, quietly, on whatever surface happens to be waiting for it. You've spent this stretch of time walking alongside some of the strangest, most carefully verified ideas humanity has ever worked out, and none of it demands anything further from you now. No test, no follow-up, nothing to carry forward except, perhaps, a slightly softer, slightly more spacious way of looking up the next time you happen to find yourself under a clear night sky. So let that settle now. Let the equations fade. Let the names and the diagrams blur softly into the background, the way distant stars blur when your eyes finally start to lose focus. Let your breathing slow. Let the tension in your shoulders unwind, the weight of the day finally lifting off of you. Space-time is curving gently around you right now, patient and unchanging, exactly as it has been the whole time, exactly as it will keep being long after you're asleep. There's nothing left to do here, nothing to solve tonight. Just rest inside a universe that is, in its own quiet and endlessly strange way, holding you exactly where you are.